This is a review of Microcode for the second exam in COMP375 Computer Architecture and Organization at North Carolina A&T State University. Gotta have a quote. The second exam in COMP375 is Wednesday, March 18th. Starts at 11 and will be done by noon. You ought to start at 11 because it will be done by noon. You must be logged on to Blackboard at that time. There are several topics covered in the exam. Digital logic, VLSI, cache, memory types, and microcode, which is the topic of this review. Microcode is in chapters 16 and 19 of the online textbook. If you read the textbook and you find topics that are not on the exam, well, you'll learn more, but they won't be on the exam. If, though, we've mentioned any topic in class, it could be on the exam. This is an online exam, so you can use your book, your notes, or search the web. The exam will be problem-oriented, so it's not likely you'll find the answer directly on the web or anyplace else. Here is our simple CPU for microcode. The bus, which is the horizontal line on the bottom, is connected to multiple registers. There's two user registers, a program counter, which always contains the address of the next instruction to be executed. The instruction register, which contains the currently executing instruction. The arithmetic logic unit, or ALU, which does all the arithmetic. It has two inputs. One comes from the bus and one comes from the operand register. When it does arithmetic, it puts the result in the result register. The interface to the memory system is done through two registers, the MAR, or memory address register, and the MBR, or memory buffer register. If you want to read something from memory, you put the address in the MAR, tell the system to read. Now the memory system is slower than the microcode, so you'll have to wait, but when the wait is complete, the results you wanted to read will be in the MBR. If you want to write data to memory, put the address in the MAR, the data you want to put in memory in the MBR, and then tell the system to write. The microcode implements the fetch execute cycle. So the first step is to fetch the instruction from memory, or go out and read that memory address. And of course, the program counter always contains the address of the next instruction to be executed, so that's where it will read. You then have to increment the program counter so it doesn't keep executing the same instruction. Once the instruction is in the machine, then you'll have to get the operands. They may be in memory or in another register or immediate. After you've got all the data and all the operands, you have to execute the instruction through the ALU, and then you store the results back into a register. Only one register can put a value on the bus at a time. That means that only one of the columns that has the arrow to bus can be checked at any given time. Putting a value on the bus means charging up the bus wires to either voltage or down to ground. This can only be done by one value, otherwise a short would result. Multiple registers can copy a value from the bus. So if you want to copy a value from register A to register B and register C, A can put the value in the bus, and both B and C can copy that value at the same time into those registers. When you access memory, you have to do a memory read. You do not have to do a memory read if you're getting data from a register. The memory read is, as the name implies, only for memory. Note also that in the 3 lines of the instruction fetch, the last line puts a value into the instruction register. This is the only time you ever put a value into the instruction register. If you put a value in the instruction register on some other line of microcode, it'll be easy to grade. It's wrong. Here are 3 lines that do the instruction fetch and program counter increment. This is done for every instruction. The first line copies the program counter value into the memory address register. The program counter always contains the address of the next instruction to be executed. And so it's going to read from that memory location. At the same time it's reading, it will also copy that program counter value into the ALU and increment it, so that we don't always fetch the same instruction. The second line of microcode copies that incremented result onto the bus and back into the program counter. At this point we have to wait for memory, so after the wait is done, the instruction that we're reading is in the memory buffer register, which we copy to the bus and into the instruction register. Every instruction starts with the instruction fetch in the program counter increment. In many of the assignments, we only bother to show this once because it's done every time and it gets kind of boring to write it every time. When you do a jump instruction, such as jump to rabbit, the microcode will always change the program counter value. The program counter contains the address of the next instruction to be executed. So if you want to change what's going to be executed next, you have to load a new address into the program counter. Typically, the program counter is changed as the last instruction of the last microcode instruction for a jump. Jump instructions don't usually access memory unless you are pushing or popping something on the stack. Arithmetic instructions, add, subtract, multiply, divide, have a pretty standard format. The first thing you do is you copy something into the operand register, typically from a register or perhaps from memory. The second value is put on the bus, next step, and you execute the instruction, you add or subtract. That puts the result in the result register, which in the third line is copied back to someplace else, usually a register. In a real computer, the actual instruction to be executed would be determined by the opcode of the instruction. In our simple microcode, we specify it as an ALU function. Here's an example of a direct memory access instruction that's going to go out to memory, get the address of, or get the value in cow, and subtract that from R1 and put the result in R1. Because the operand is in memory, the first thing it must do is copy that address of cow into the memory address and start reading. The next line we're going to wait because we need that cow value, but before we wait, we'll copy R1 into the operand register to get ready for the subtract. When the memory value is available in the memory buffer register, we'll copy that onto the bus and into the ALU, telling the ALU to subtract. We then copy the result from the result register back on the bus and into R1. Try this one. Try writing microcode for a jump, or that is a function call. A stack-oriented function call, just like Intel and most other machines do, where it's going to save the return address on the stack and jump to the start of the function. The return address is what's in the program counter because the program counter always contains the address of the next instruction to be executed. So all you have to do is push the program counter value on the stack and then jump. You might pause the video for a minute while you think about this. All right, here's the answer. On the first line, we're going to do the push. So we get R2 as a stack pointer, and we put that on the bus and increment it. R2 is pointing to the top of the stack, and we want to put something else on top of that. We have to increment the address so it points to the value on top of the current top of the stack. The second line, we take that result, put it back into R2, so R2 is always pointing to the top of the stack, and also copy it into the memory address register, where we're going to write the return address. The third line, we get the return address from the program counter, put it into the memory buffer register, and tell the system to write. So now we have written the return address onto the stack, and the only thing we have to do less is jump to the start of the method. So we copy the method address out of the instruction and put it into the program counter. For more help on microcode, you can look on the website williams.comp.ncat.edu/COMP375. There are examples, including some examples where I've explained why each step is taken. There's also the microcode animator. The microcode animator will allow you to step through your microcode, and it will try to capture as many errors as it can detect. On the exam on Wednesday at 11 o'clock, there will be questions asking you to write microcode. You'll be asked to simplify logical expressions. We're probably not going to draw logic diagrams because I haven't figured out how to do that online. You will be asked to select the proper memory for an application and compute the average memory access time for either paging, caching, or both. Good luck on your exam.